Okay, this will be an introduction to implicit differentiation. Okay, let's think about the following question. Find the equation of the tangent line to the circle x squared plus y squared equals to 5 at 3 comma negative 4. So let's try to solve this question. It's an easy question because it doesn't require implicit differentiation, but I can show you a method that uses this thing called implicit differentiation, and hopefully you're sold after I give you this example. Okay? All right. So first, solution 1 is you solve for y squared. Here's a radius 5 squared. Oh, I meant 5 squared. Okay. Radius 5 circle. And 3 comma negative 4 is where? 3 comma negative 4, it's over here. This is 3 comma negative 4. And we're trying to find the tangent line at this point. And because tangent lines require the slope, and slopes are obtained by finding the derivative, we better solve this for y to figure out what dy dx is. Is that clear? So far so good, right? So now what should I do? What should I do here? Yeah?
Take the square root.
Okay, here you have to be careful. Should I take the plus or minus? See, whenever you take the square away, you need both plus and minus. Don't forget this, okay? Should I take the plus 1 or minus 1? Why the minus? Because plus 1 describes the top circle and the minus gives you the bottom circle, right? You get two equations because you get one equation per half of the top and bottom, right? The top circle gives you the plus 1, bottom circle gives you the minus 1. And because this point that we're trying to figure out is in the bottom half, we need to choose the minus 1. So from here, we choose y equals to negative square root of 5 minus x squared. And from this, we have to differentiate y prime. Okay, and then 5 minus x squared, when you put it out and differentiate, it's this negative 2x. 2 cancels, negative becomes positive, so you have x over, sorry, this should be 5 squared. Forgot that, okay. I have square root of 5 squared minus x squared. Okay. And then I have to evaluate y prime at x equals what? I'm trying to find the slope at this point, right? So in order to get the slope, what should I put my x to be? 3. So you have 3 over square root of 5 squared minus 3 squared. It's 3 over 25 minus 9, that's square root of 16, which is 3 over 4. And at the end of the day, you have the slope 3 over 4, point 3 comma negative 4. So if you use the point slope form, it's y minus negative 4 equals to 3 over 4, x minus 3. That's the answer. If they want the slope-intercept form, you should solve for y, but it's not that hard. Okay. So that's one solution. Any questions so far? Okay, then let's try to do this second method, solution 2. Now the second method is a way to find y prime in a rather lazy fashion. Okay, so you want to somehow be lazy but still get the prime. You know how many advances in science and technology is because of people just trying to be lazier, make it more convenient. Right? So in order to be really lazy and still be successful, you have to think smart. Okay, you have to use your head. All right, so that's what we're trying to do. Okay, so I think the most horrible part of this first solution is having to deal with the square root, and my goal is to somehow avoid having to take the square root and still solve it. Right? Now, to make you understand what the method I'm about to introduce to you, it's instructive if we try to do the following. So right now, let's not go to solution 2 right away. Let me give you a baby problem to think so that you understand what implicit differentiation actually does. So first of all, if you had a function and you squared it and you differentiated it, what will be its derivative? What rule do you have to use? Chain rule. Okay, so 2 comes down, right? F of x. And then you differentiate f of x because that's the inside function. So you get f prime of x. Okay? That's how you differentiate f of x squared, right? Assuming that you know what f of x is and f prime of x is. Okay? Now think about something similar to this. Let's say y is a function of x. Okay? And you have y squared, and you're differentiating this by x. Okay, so a little clarification here. Here, this prime, this derivative, this prime here really means d dx. You're trying to differentiate by x, while y is a function of x. Okay? All right. So what would this be? Can you tell me? So even though this doesn't look like a nested function, you should really think of it as a nested function. Y is like really the function of x, right? Nested inside the square function, so you have to apply the chain rule. So what does that give you? I'm waiting because this is really important. I want you to think about the answer. Yes?
2y minus dy dx.
Okay. It's 2y y prime. Where does this y prime come from? From the fact that y is actually a function of x, right? And you're trying to differentiate y by x. If this prime was differentiation by y, then it would just be 2y. You don't have to do this next thing. But because we're trying to differentiate by x, the nested function y should be pulled out and differentiated, just like when you differentiate this. Does this make sense? Should I do another example of such a thing, or is this okay? This is okay? All right. Okay, so now let's try to apply this to what we have here. Here we have x squared plus y squared equals to 5 squared. Now, before, in the previous solution, we solved for y and then we differentiated, right? Here, we're going to do something outrageous. We're just going to differentiate it without solving. But, when we are doing it, we have to keep in mind that y is actually this thing, okay? As it is, it looks like y is just y and x is x, but in reality, what's hidden in this calculation is that we're really thinking of y as a function of x, just like this. It's some f of x, right? Okay? So when you differentiate y squared with respect to x, you need to do something like this, okay? So let's differentiate both sides. We're going to take this equation, differentiate the left side, and differentiate the right side. Let's see what happens. Then derivative of x squared is 2x. Derivative of y squared is 2y y prime. Because y is a function of x, you have to apply the chain rule, so y pulls out and you have to differentiate it. Okay? And the derivative of 5 squared is 0. Yeah, it's very easy to confuse yourself and say, oh, it's 2 times 5. No. Yeah. This is a constant, so you differentiate it, you get 0. If you really wanted to use the chain rule, you can. You can bring the 2 down and 2 times 5 to the first power times, and then because of the chain rule, you have to bring the 5 out and differentiate. But 5's derivative gives you derivative of the 5 gives you 0, so you still end up getting 0, even if you apply the chain rule. Okay? So this is what you get. Now let's try to solve for y prime. First, 2y y prime is negative 2x, and divide by 2y both sides, so that 2 cancels, and you get negative x over y equal to y prime. Now, why do we need to solve for y prime? Because y prime gives you slope. Yeah, we're trying to solve this question still. Okay, we're trying to find the slope by plugging in the appropriate values for y prime. So when I need to figure out the slope when x is what?
0.
Here. X is 3 and y is? Negative 4. Yes.
Oh, it's not like the horizontal line.
No, we're not trying to solve for horizontal tangent or finding the maximum or minimum. Here, we're just trying to find the slope at a given point. Therefore, those values should be plugged into our derivative. Okay? So, what does that give us? It's negative of 3 over negative 4. Negative cancels, so you get 3 over 4. And hey, look at this. We got the same slope as before. Okay? With much less effort, because we were playing smart. Okay? Yeah. We like this, right? Yeah. We like being a little lazy but smarter. Yeah, that's always the better way. Okay? So we do this, and therefore the final answer is you get y minus negative 4 equals to 3 over 4, x minus 3. For the same reason, it has to pass through this point. It has to have this slope, and I'm using the point slope. So you get the same exact answer with those both methods, but in the second method, we avoided having to solve for y. The only catch is that you still have to remember that when you're differentiating y is a function of x. If you keep that in mind, then you're allowed to just differentiate as it is and still get the right answer. That's what we call implicit differentiation.